Hi, my name is Greg Smith, aka Dr. Frankentosh, and today we're going to look at my Raspberry Pi Pico binary clock. So when I was a boy in 1978, I was an electronics hobbyist, and I'd built some bizarre circuits, and I'd present them to my mother, to which she would just humor me as I explained what the heck I was building.
Told me what it would do, and it was really neat, but it looked like a bunch of wires and bulbs and things, and it looked like something from outer space.
And it came to pass that one of my classes, one of the shop classes, we're doing an electronic segment, and we were supposed to build something.
It's all right with me, but Greg, please make something that, is like in a box, like a radio type, where all those wires and things that I could set it out and
Say my son made that.
show it.
With all these lights on it, and it didn't have a regular face on it, and it didn't have digital numbers on it, but it had individual lights that were either on or off, and it was called a binary
I
clock.
said, okay, I'll give you the $40. You make sure it's in a box. So he made me a clock, a binary clock, and I still have that today, and it's still a conversation piece.
It still works.
And it still works, and everybody asks about it, and we tell them how it works, and I still like it just as much as I did that day, and especially because Greg made it, and it's in a box.
So here's the original clock, maybe a little bit difficult to see from this picture, but there are 18 LEDs. The first column is for the hours, the next two are for the minutes, and the final two are for the seconds. And you can decipher how to read this clock with the sticker that's on the bottom of the clock. So on the back of the clock, there are three buttons, a black one for disconnecting the pulse to the main board, which will cause it to pause while you wait for the seconds to catch up with whatever you've set it to. The middle button is the slow button, which cycles through the seconds very fast, but not super fast. And then finally the fast button. Basically, the fast button is for setting the hours, the middle button is for setting the minutes, and then the top button is to pause the clock while you while the seconds catch up with whatever you've set it to. So here's the circuit board that is offending. You can see the crack here in the middle. This is where the transformer was connected to the board, and it therefore made it the weakest link in the entire board. And so these wires up here are an old attempt I had at trying to fix this, which ultimately failed. And here you can see the original LEDs in their original circuit board. Sadly, one of the LEDs, this one here, had failed, and it had to be replaced. Now, I could not find an LED to replace it perfectly. I found one of the same size, but it was brighter. Now, because this LED was significantly brighter, the current limiting resistor that went to this, which was only 110 ohms, was swapped out with a resistor of 10K ohms. And I did try to salvage all of the original resistors to drive the board, and that worked out pretty well. So here's the original, what I call heartbeat board. This board had an input from over here from the power, and this would be cycled into these decade counters, which are 7490s, which were designed to divide the line voltage frequency of about 60 hertz down to 1 cycle per second. Now, this was also set up to run in the UK, so you can see over here there's a jumper for 60 hertz and another jumper for 50 hertz. So these 7490s would count from 0 to 60 and then recycle. These are 7408s, which are quad NAND gates, and over here are 7432. These were used to detect when the counters got to the right value and would cause it to reset. So the whole idea here was that 60 or 50 hertz would be going into these decade counters. The decade counters would then divide the line frequency down to 1 cycle per second, and then this red wire would send that 1 cycle per second back to the display driver board. Here we have the main logic board. Over on the left here are the seconds counters. These are 7490 ICs. They count from 0 to 9. This one here counts from 0 to 5 and then resets. This one counts from 0 to 9 and resets. And so between them, they do the 60 seconds. And these then feed the LEDs on the LED board through current limiting resistors of 110 ohms each. These feed the minutes counters. This is the tens of minutes and then the ones of minutes, which then upon recycling feeds this 74197, which is a binary counter that is up to 12 and then reset back to 1, so that counts the hours. And of course, these all drive the LEDs on the LED board directly through 110 ohm resistors, current limiting resistors. Of course, over here you see the big old power supply, which was a step down from 120 down to 5 volts. And here is the capacitor, and I think those are Zener diodes, which are half-wave bridge rectifiers. I don't see it here, but there's also a 5-volt power regulator. So that's pretty much the entire clock. So for the upgrade, I had 7 goals. The first was to maintain as much of the original clock as I could. So I wanted to maintain the original case, the original LEDs, and the original hold, slow, and fast switches. I was able to salvage all of the 10 ohm resistors. But what I wanted to add was the ability to set the clock using an iOS Bluetooth app, and also possibly set the time from WWVB, which is a radio station in Colorado, which is constantly broadcasting the current time across all of the United States from the National Institutes of Science and Technology atomic clock. Another goal would be to set the clock using Internet Network Time Protocol, or NTP. And finally, to be able to store some settings on the persistent flash store so that if we lost power, it would come back. For example, our location on the United States, because it takes time for the WWVB atomic clock signal to reach us, and you have to adjust whatever time you receive to compensate for that. Also, daylight savings time or not, and whatever other settings I might want to put in there. So to do all this, I wanted to use the Raspberry Pi Pico W. This is a very capable microcontroller. It has a RPi 2040 microprocessor, as well as a number of other circuits. It has 26 GPIO pins. We'll be using 18 of them for driving the LEDs, and 3 of them for reading the switches. And then this silver circuit is Wi-Fi and Bluetooth, so we'll be utilizing that as well. And we'll be programming it in MicroPython. I had considered using CircuitPython, which I consider to be superior, but it doesn't drive the Wi-Fi chip, so we can't use it for Bluetooth. Adafruit are the folk who deliver CircuitPython, and they have their own Bluetooth chip, which they are focusing on. Also, I'll be using Adafruit's Bluefruit controller, which is a general-purpose Bluetooth iOS app. I believe it's also available for Android, and we'll be using that to create a CLI interface to reset the time on this processor. Here's a picture of the atomic clock. I was really pleased with this. I thought this was going to be much bigger, but I hope you can see from the comparison to the keyboard, this is a very small clock receiver, so I'm really excited about having this added to the project. So the first thing I wanted to do was salvage the LEDs, and I added a ribbon cable. One piece of the ribbon cable went to hours, another piece went to seconds, and another piece went to minutes. And then I also salvaged the resistors that went with it and tested these out. Of course, as I mentioned earlier, one of the LEDs had failed, and so I swapped in a brighter LED, and we'll see how I fix that later. Breadboarded the entire project, putting the Raspberry Pi on my breadboard. And then I went to my local group called Hack RVA here in Richmond, and they had a nice Radio Shack. It's a perf board, which is the same pinout as my breadboard. So that's very handy. Here you can see I've salvaged all of the resistors and also the header pinouts here for the radio, the ribbon cable. And I don't know if you can tell here, but this one LED is slightly brighter than all the others. When it's running, it's really not that noticeable. So I was very pleased with the results on that. I had tried to run this using battery pack, and in the end, it only lasted for 1 day. So at some point, I'm going to have to add some sort of 5-volt power supply that I can use. So here's what it looks like when it's all put inside the box. The circuit board here fit very nicely. I was running on batteries and the back, and I also shined up the box using WD-40, which is my favorite solvent these days. It seems to be a cure-all for almost all ills, and really pleased with the results. To do the programming, I used a Apple MacBook Air, which I call my slab top. This particular Air came to me with a broken display. I removed the display and I connected to my wall-mounted 43-inch monitor, and this makes for an outstanding programming environment. I will be featuring the slab top in future videos, but for economical space, this is just outstanding. Here's a picture of me resetting the clock using the Bluetooth app from Adafruit called Blue Fruit, and that pretty much covers the project. I can set the time, I can turn debug on or off. With debug turned on, I can set the delay to any value, and that will drive the clock faster so I can test all the LEDs. So I'm very happy with the results. I still have a few things to iron out, including the power supply and the WWVB atomic clock reader. But for now, I feel like I've upgraded and restored my mom's favorite hardware project, and this was something that we shared over my entire life, and so very happy to have this back on my mantle and working again. So thanks very much for watching. Please don't subscribe to my channel, don't watch my other videos, please don't look at my other channels. Your time is valuable. It's been wonderful having you here. Please have a great day, and I'll see you next time.